To today's Friday Math Happy Hour. Today we're going to be covering exponents, exponential equations, and logarithmic also equations. Okay, these are the topics that I'm going to cover today. We're going to cover exponent properties. The exponent properties are mostly for the NCBN 0324, okay, which will also help the students taking the Math 1324. We're going to cover those exponent properties, converting radical expressions to exponential expressions and vice versa, simplifying radicals, exponential functions and graphs, writing exponential equations into logarithmic equations and vice versa, graphing logarithmic functions, and also how do you apply them in real life application problems. So to start off, these are the exponent properties. I believe there's about 10 properties that we have to come familiar with. Okay, now this is like the concept. If m and n and p are integers and a, b are real numbers, then this is number one, the product rule. If you have a to the m times a to the n, right? But in other words, the a is the base. So if you have the same base, then we get to add the exponents. That's called the product rule. This is a quotient rule. If you have the same base, right, but you're dividing like a to the m divided by a to the n, then it's going to be a to the n minus n. You subtract the exponents. And a cannot be zero because if a is zero, it'll be undefined. This is called the power rule. If you have a to a power, like a to the m raised to another power, you multiply the powers. This is called the power of a product rule. If you have a times b to the n, then it will be the same thing as a to the n times b to the n. And I'm going to show an example or examples of each one of these properties, I believe, in the next slide. And furthermore, if you have a to the m times b to the n raised to the p power, right, it's going to be a to the m times p times b to the n times p. This is called the power of a quotient rule. If you have a divided by b to the n power, it's going to be the same thing as a to the n divided by b to the n. And b cannot be zero because if b is zero, the function will be, the expression will be undefined. Also, if you have parentheses, right, a to the m divided by b to the n, all raised to the p power, then it's going to be a to the n times p divided by b to the n times p. This is a negative exponent rule. If you have a to the negative exponent, like a to the negative n, you make it positive by doing the reciprocal, so it'll be 1 over a to the nth power. And again, a cannot be zero because if a is zero, it's undefined. And also, guys, here's what I meant about the reciprocal. If you have a divided by b to the negative n power, you do the reciprocal and you make it positive. And this is a zero exponent rule. This rule, you're by surprise how many students, they don't know this rule. Even in calculus 1, calculus 2, they say that if you have a to a zero power, they say it's zero, but that's wrong, it's 1. So always remember that anything to a zero power will always be 1. And a cannot be zero. Now this is a fractional exponent. If you have also this, students use this for the upper level math courses, say, for example, for the 1325, when you take the business calculus. This also, you need to know these rules here, especially rule number 6 and rule number 8. If you have a raised to the fraction exponent, a divided by n, then it's going to be the nth root of a to the n power, which is equal to the nth root of a close parentheses to the nth power. All these are the same thing. Okay. Now let's start with the product rule. Okay, now here's an example of the product rule. So you have a to the m times a to the n equals to a to the n plus n. Example. The a is the base and the m is the exponent. Must have the same base to apply the rule. Right? We have the same base, so x cubed times x squared. This is like the long way, just so you see what's taking place. Okay, but we're not going to do it this way. We're going to be applying the rules. But for example, x cubed times x squared, right? The x cubed is in blue, so it means like x times x times x. And the x squared in green means x times x. So if you have x times x times x 5 times, right, it's going to be x to the 5th power. In other words, by applying the rule, right, you have the same base, which is x, you add the exponents. So we can go straight from here, from x cubed times x squared all the way to x to the 5th power, because you can do that in your heads. For example, x to the 7th times x to the 3rd will just be x to the 10th, right? They have the same base, equals x to the 10th power. Number 3, x squared times y to the 4th. If you notice, number 3, they're not the same base. The base, the first base is going to be x, and then the second is going to be y. So this one cannot be simplified. So it will just be x squared times y to the 4th. They have to be the same base in order to apply the rule. Now this one here, right? If you have parentheses, 5x to the 4th, close parentheses, times parentheses, negative 3x squared. Here, right, you're going to multiply the coefficient, so it'll be 5 times negative 3. And then we have the same base, so we're going to add the exponents. So it'll be negative 15x to the 6. But you can go straight from here, guys, to the answer. Okay? Again, let's do the previous one. You can do this in your head, right? Because 5 times negative 3 is negative 15. And then we notice that we have the same base, which is the x. We add the exponent, so you can go straight from the original problem all the way to the answer. Here in the middle, I'm just showing you how to get that answer. Okay. Okay, for example, this one here. What's negative 2 times negative 3 is going to give us 6, right? We have the same base, x and x, so we're going to add the exponents for the x's. So it's going to be 2, it's going to be 6 x to the 9th and y to the 5th power, right? And here's how you do the work, or here's the explanation, right? So it's going to be 6 x to the 9th, y to the 5th. Now this one, we're going to go straight to the answer. What's negative 5 times 6? Negative 30. We have x on the left one, we have x on the right, so 1 plus 3 is 4, so it's going to be negative 30 x to the 4th, y cubed. Okay, now about this one here. Let me go back real quick. 3 times 8 is 24. We have x to the 4th times x to the 5th. Again, we add the exponents. It's going to be x to the 9th power. We have y cubed times y. This is like a 3. This is like a 1. So it'll be y to the 4th. So the answer will be 24 x to the 9th, y to the 4th. Now let's do the quotient rule. So again, when you have the same base, right, but you're dividing the same bases, you subtract the exponents. For example, x to the 5th times x squared, they have the same base. We apply the rule, so it'll be x to the 5 minus 2, which is equal to x to the 3rd power. Number 9, x to the 10th divided by x to the 7th, it'll be x to the 3rd power, because you subtract the exponents. Number 10, x to the 4th divided by x to the 8th is going to be x to the negative 4. And most of the times, they don't want you to have negative exponents, okay? But we're not there yet. I believe it's rule number 8, I think, when you have negative exponents, we're going to do something to them. But for now, let's put that on hold for now. For now, this is your answer. Okay? That's rule number 6. Let's go to this is rule number 3. Now, I believe this is already self-explanatory. Let's do rule number 3. The power rule, when you have a to the power raised to another power, we multiply the powers. Right, for example, number 11, we have x cubed raised to the 2nd power will give us x to the 6th. Or this can be the same thing. If you break it down, it's going to be x cubed times x cubed, which would be x times x. This is a breakdown completely. Just so you see that we can go straight to the rule, right? If we apply the rule, it'll just be x cubed raised to the 2nd power will give you x to the 6th power. But here in the middle, I just broke it down even further. But you can go straight from the question to the answer. We see this is a property. We multiply them, x to the 6th power. Now this will be negative x to the 4 squared. This is the same thing as x to the 8th power. Okay, why is that? Because when you raise a negative to the even power, it's going to be positive. This is the same thing as x to the 4th. Negative x to the 4th and negative x to the 4th. So negative times a negative will give you a positive, so that'll be x to the 8th power. Number 13, we have negative y squared to the third power. Now, since this is negative, right, and is raised to the third power, to the odd power is going to be a negative, because any negative raised to an odd power will be negative. This will give you negative y to the 6. Let's break it down. Okay, this will give us a negative y squared times negative y squared times negative y squared. Negative y squared times negative y squared will give you y to the 4th. Then when you multiply it times another one, right, it's going to give us negative y to the 6th. Okay. There's different ways to get the answer, right? But there's always going to be one answer. But there's different ways to get there. Okay, you use, in my opinion, it's better to use the rules. Now let's do the power of product rule and the power of a product rule. Okay, now if you have a times b to the n, it's going to be a to the n times b to the n. Here are some examples. For example, x times y squared will be x squared times y squared by applying that rule. This will give us 2 cubed times x cubed, which will give us 8x cubed. This will give us x to the 6, y to the x, right? Because we're going to be multiplying. You see, you multiply the 2 times 3 and the 2 times 4 because this is a power raised to another power. This will give us what? This will give us negative 3 to the third power, x to the 6, and y to the third power. Negative 3 to the third power will give us negative 27 because negative 3 times negative 3 times negative 3 will give us negative 27. And then here we apply the power of the product rule. 3 times 2 is 6, and 3 times 1 is 3. But let me break it down even more. Let's do it 3 times, right? There's once, there's twice, there's 3 times. So negative 3 times negative 3 times negative 3 will give us a negative 27. We have x squared times x squared times x squared, so we add the exponent. So 2 plus 2 plus 2 is 6. We have y times y times y will give us y to the third power. Or, right, the same thing as negative 3 to the 1 times 3, x to the 2 times 3, and y to the 1 times 3. That'll be negative 27, that'll be x to the 6, and y to the third. Like I said, there's different ways to reach the answer. Okay, but there's always going to be one answer for these. Number 5. This is called the power of a quotient rule. If you have parentheses a divided by b to the nth power, then it's going to be a to the n divided by b to the n. Example, by applying the rule, this will give us x cubed divided by y cubed. Now this one here, right? We have, it's going to be x to the 2 times 5 divided by w to the 3 times 5. So we're going to give us x to the 10th and y to the 15th. I mean w to the 15th. Like I said, you can go straight from the original problem to the answer right away if you know the rules. But if not, you can break it down, even like we did on number 17, break it down to the extreme so that way you can understand it. Now comes the negative exponent rule. If you have a to the negative n, you put 1 under a to the n, and it becomes the exponent becomes positive. Example, by applying the rule, this will give us 1 over x to the 5th power. 3 to the negative 2 will give us 1 over 3 squared, which will give us 1 over 9. Now remember this one, guys, right? So we're going to apply the rule first, right? We invert it. Remember the rule, I think it was slide number 2. We use a reciprocal and make it positive, right? Which will give us y cubed over x cubed. Here's how. Remember that you put it, you're going to put 1 over x to the y and make it positive. Now this means that is 1, that's a 1 there, right? So this division becomes multiplication. And the bottom fraction, we use a reciprocal. Flip it and it becomes positive. I mean flip it, right? And the 3 goes like that. So it's going to be y over x cubed. It'll be y cubed over x cubed. You can go straight from here to the answer. and then you simplify it. Okay, this is crucial to know that once you have a fraction to the negative exponent, all you do is do the reciprocal and make the exponent positive. Okay, now let's apply the rule, right? Reciprocal will be 5 over 2, and the exponent becomes positive. Now we can simplify it, so it's going to be 25 over 4. Now comes the rule number 7, the zero property rule. If you have a to the 0 or a to the anything to the 0 power will always be 1, and a cannot be 0. Example, what's x to the 0? 1. What's parentheses 5x, y, z, close parentheses to the 0 power? The answer is 1, because the whole thing, this whole term, is raised to the 0 power, which is 1. Now comes rule number 8, which is the last rule, the fractional exponent rule. If you have a to the power of m divided by n, the n becomes your index, and the a is a radicand, and the n becomes your exponent, right? I mean, the n becomes the power. Again, here's what everything is. Here's what everything means. For example, the n is called the index or the root. The a is called the radicand, which is the base, and the m is the exponent, which is a numerator. That's a radical symbol, which is the root here. That way you know the terms, what they call, okay, with the vocabulary. Right, so a to the m over n is equal to the nth root of a to the n power. Let's do number 26, okay? Let's convert it from exponential to a radical. This will give us the cube root of x by applying this rule here. Number 27, this will give us the 5th root of x cubed. This, right, the whole 3w is a radicand. So it's going to be the cube root of 3w squared. Now this one, we're going to go the opposite way, right? So they give us a radicand, now we have to put it into exponential form. So the 8xy is going to be the base, right? This is going to be the a. The n will be the index. The 2 will be the exponent. The 2 will be the m, the exponent. So now it's going to be 8xy with parentheses to the power of 2 over 7. Okay, that's how you break it down. So they will give us 6x with parentheses to the 1/4 power. Now here's a common mistake that students make. Okay. They put it in this form. Because this is not the correct answer, from the original. This means that only the x is to the 1/4 power, okay? Please be careful here, guys, okay? Because this is what it means. This is what this means, you see? And this is not like the original, like the one over here. Only the x is to the 1/4 power, not the whole, the 6x term. So please be careful with this. This is a common mistake that students make. Now, simplifying radicals. Okay, for simplifying radicals, you need to know some of the roots. For example, some of the square roots, the cube roots, and the 4th roots. Let me show you what I'm talking about. These are square roots, okay? So you have to know these. The square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, and so forth, right? Try to go all the way to 10, to 100. So know these. This is crucial to simplify radicals. And the cube roots, the cube root of 1 is 1, the cube root of 8 is 2, the cube root of 27 is 3, the cube root of 64 will give us 4, maybe know all the way to 5. The cube root of 125 will give us 5. I need at least know these many. Now for the 4th roots, the 4th root of 1 is 1, the 4th root of 16 is 2, the 4th root of 81 is 3, and I believe that's all you got to know up to there. Okay, but the more that you know, the better. Okay, now how do we simplify radicals? Okay, is 24, is the square 24 a perfect square? You see, it's not. It's between the 16 and the 25. So how can we simplify this? We have to get all the factors of 24. How can we get 24? Right, this is not a perfect square. So how can we get 24? 1 times 24, 2 times 12, 3 times 8, and 4 times 6. From all these factors, which one's the highest perfect square? It's going to be 4 and 6. The 4 is a perfect square. So it's 4. So I'm going to use this combination. So the square root of 24 is equal to the square root of 4 times the square root of 6. Right, so we can separate them. The square root of 4 will give us 2. So the square root of 24 is equivalent to 2 square root of 6. This is the answer that they want. Okay, that's your solution. That's how you simplify radicals. Okay, that's your answer, 2 square root of 6. Now this is already 1324. Everything that are covered up to this point, that's for the NCBN, for the NCBN 0324. But it's good to know most of those rules because you're going to be applying them in this course and also for the 1325 course. Examples of exponential functions. If you notice, the variable is going to be the exponent. You see, so all these are exponential functions, examples of exponential functions. Okay, now recall the a to the m time behind, right? So this will be f of x equals to a to the x. X, right, is a base. The exponent is a variable or letter frequently x. Okay, so this is an exponential function, a base raised to a variable power. And a has to be more than 0 because if it's 1, 1 to the any power will always give you 1. Okay, now here, guys, we're going to have to know how to evaluate exponential functions in order to be able to graph them. So, for example, it says find f of x when x equals to -2, -1, 0, 1, 2, and 3. So let's do a little table. -2. So when x is -2, right, we're gonna go into the function. We're gonna plug in -2 for the x. So now we're gonna use the negative exponent rule, right? We make it positive by doing put it 1 over 2, and the exponent becomes positive. It's gonna give us 1/4. So when x is -2, y or f of x is 1/4. When it's -1, right, we apply the same concept here. So it'll be 2 to a -1 will be 1 over 2 to the first power, which will give us 1/2. So when x is -1, my f of x or my y is equal to 1/2. Now we're going to apply the 0 power, the 0 exponent rule. Anything to a 0 power will give us 1. So when x is 0, y is 1. Now let's try 1. When x is 1, right? So 2 to the first power will give us 2. So when x is 1, my y or f of x is equal to 2. And let's try 2. We're going to evaluate f of 2 means it's going to be 2 to the second power will give us 4. So when x is 2, y is 4. And finally, 3. When x is 3, we evaluate the function f of 3, which is equal to 2 to the third power, which will give us 8. Because 2 times 2 times 2 will give us 8. Now we get to graph the function. Here's a graph of an exponential function. Every graph of an exponential function in this form will be how it looks like. This is called the parent function. The parent graph. This is a parent function. Right now, on the next slide, the bigger the base, the more it's going to go towards the y axis. Okay. These are for exponential growth. Okay. And here are the characteristics. The graph is above the x-axis, right? Here's the x-axis. The y-intercept will always be 1. The graph climbs steeply to the right, right? It goes steeply to the right. The negative x-axis is the horizontal asymptotes. You see this is a negative x-axis. That'll be the horizontal asymptotes. The larger the base A, the more steeply the graph rises to the right. So the bigger the A, the more the graph goes to the right, to where the y-axis is. It's just an example. Here's the one that we did earlier, right? Y equals to 2 to the x power in green. You see if the base is 3, it goes a little bit steeper. If the base is 10, it's a little bit steeper. If the base is 100, it's going to be very, very steep. So the bigger the A, the base, the more steeper it gets. Now comes the one that are exponential decay. Here's how the graph looks, and these are the characteristics of the graph when A is between 0 and 1. Okay, and here it is, right? So for example, the graph is above the x-axis again. The y-intercept will always be 1. The graph falls sharply to the right. The positive x-axis is horizontal asymptote, right? This is my horizontal asymptotes. The smaller the base, the more steeply the graph falls to the right. See? So, right, this is, say, so 2/3, right? So 2/3 in purple, 1/2, 1/3. So the less the exponent is on the fraction, the more it goes to the right. See, it goes from 2/3 to 1/2, which is less, and less, so it gets closer and closer to the y-axis. So these are the characteristics. Okay, now what happens when you have a negative exponent? Right, we have to make it positive. So 1 over 2 to the x power is the same thing as 1/2 to the x power. Remember, guys, that we can use the reciprocal, right? Isn't 2 to a negative 1 the same thing as 2 over 1 to the negative x, right? The reciprocal of 2 over 1 will be 1/2, and we make it positive. So let's graph g of x equals to the 1/2 to the x power. Here, guys, right? So here, if it's -3, it's going to give us 8, but let me show you how it's done, right? So if we plug in -3, right? We're going to invert it, and it becomes positive, right? So it'll be 201, so it's going to give us 8. And we repeat the process for other x, for the rest of the x values here. And this is what we get when it's -2. It's going to give us 4, and so forth, right? And the graph will be exponential decay. Okay. So this will be like the function, how it looks for exponential decay when A is between 0 and 1, which is the base. The base is A. Now comes logarithms. Until the development of computers and calculators, logarithms were the only effective tool for large-scale numerical computations. No longer needed for this purpose because now we have calculators and computers. Okay, but in the past, that's the way they used to calculate real big, large-scale numerical computations here. So definition of logarithms to the common base. The basis will be 10. For example, you have y equals to log of base 10 to the x is the same as y equals to log of x. If there's no base, guys, like here, we know it's base 10, okay? Which means 10 to the y power equals x. So this is called logarithmic form, y equals to log of base x, of x, which means this is called exponential form. So we're going to be going from logarithmic form to exponential form and vice versa. Again, no base, right? Means base 10. Simplify the logarithm without a calculator. So this is how you read it, okay? Because the base is 10. To what exponent must 10 be raised to get x? Example, right? My base is 10. So to what exponent, right, must we raise 10 to get 100? Right? That's how you read it. To what exponent must 10 be raised to get 100? The answer is 2. Because 10 squared will give us 100. Right, so to what base will 10 be raised to get, what, 10,000? So the answer will give us 4. Because 10 to the 4th power will give us 10,000. Now the base is different now, right? Now the base is 7. So this is how you read this one. To what power do we raise 7 to get 49? Which will give us 2. Because 7 squared will give us 49. How about this one here? This will be 3 to what power will give me 27? The answer will be 3, because 3 times 3 will give us 3 to the third power. 3 times 3 times 3 will give us 27. Now, writing exponential equation into logarithmic equations and vice versa. Here, guys, we're going to go from exponential to logarithmic. So this is the definition of a logarithmic to the base a. Again, y equals to log of base a to the x means a to the y equals x. Here's your conversion here. Okay, it says write each logarithmic equation into an exponential equation. So here we go. We have log of base 9 of 81 equals 2. So we have to go from logarithmic to exponential. So here, guys, I have to know what my a, what my x, and what my y are. Right? We have to know all these three variables. So my a, you notice my a will be 9. Right? My a is 9. My x will be 81, and my y will be 2. Now we put it in this format. So my a will be 9 to the second power equals 81. Why? Because my a is 9, my y is 2, and my x is 81. You can use that conversion. Now we're going to write each exponential equation into a logarithmic equation. Now we're going to go the other way. 5 to the third power equals to 125. I only did one example, guys, because this will be self-explanatory. You can apply this when you do your homework. This is how you do have to know what the a is, what the x is, and what the y is. I'm also going to do only one example for exponential equation into logarithmic equation. Right. So this is in this form, right? So we know we have to know what the a, what the x, and what the y are. But this is exponential on the left. This is logarithmic on the right. So a to the y power equals x simplifies to a logarithmic form as y equals to log of base a to the x. So again, we have to know what a, x, and y are. In this case, my a is equal to 5. My y is equal to 3. And my x will be 125. Now let's go here and put in my y. Right, so my y will be 3 equals to log, my a is 5, and my x is 125. So 3 equals to log of base 5 of 125. This can also be rewritten. It can also be rewritten as log of base 5 of 125 equals 3. This is the same thing. They're equivalent. Now, it's crucial to know how to convert from logs to exponential, because in order to graph them without a calculator, you have to know the conversion. Okay? So I put here in red. In order to graph without a calculator, must convert logarithmic equation into an exponential equation. So for example, if they give you y equals to log of base a of x, we have to convert it to an exponential to be able to graph it, which is equal to a to the y equals x. Example, number 35. Y equals to log of base 2 of x. Okay? So here, guys, right, so what's my conversion? My base, right, my a is 2. And the y stays how it is, and the x stays how it is. So this is what we're going to be graphing. But now we're going to do a table. But instead of plugging in the values for x, we're going to plug them in for y, because it'll be much easier. And now we're going to repeat the same process what we did when we were graphing the exponential, right? If we plug in -2 for y, it's going to give us 1/4. If we plug in -1 for y, it's going to give us 1/2. If we plug in 0, it's going to give us 1. And we plug in 1, it's going to give us 2, and so forth, right? So this is are the points for the function 2 to the y power equals to x. And now we graph and right, so the log is in red and the exponential is in blue. If you notice, let me show you how the log is graphed. Right, when x is 1/4, right? When x is 1/4 means that I'm going to cut the unit from 0 to 1 into 4 places. So the 1/4 will be about here, right, between the 0 and 1/2, and it's going to be -2, so we go all the way to -2. When x is 1/2, right, 1/2 will be right about there. The answer will be -1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. When x is 8, y is 3. So that's your graph. And the one in blue is the one that we graphed in previous slides. Okay, so this is how you graph them. And these are called inverse of each other also. which that's another story. But for now, we'll just leave it like that. You see the f of x is in blue. The f of x equals the exponential function, and the logarithmic function will be in red. Again, it's really important for you guys to know how to convert from logarithmic to exponential to be able to graph it. Now, this is how you apply it like in real life. Okay, this is number 36. It says, the assets in billions of dollars for a Prudential Financial Incorporated can be approximated by the function AX equals to 315 e to the power of 0.056x, where x equals to 7 corresponds to the year 2007. Find the assets for the following years. So if x equals 7 corresponds to the year 2007, so then the year 2000 corresponds to x equals 0. And the year 2012 corresponds to x equals 12. So in other words, we're going to evaluate the function a. We're going to plug in 0 for x. We're going to evaluate a of 0. It means we plug in 0 for x, right? Remember, 0.56 times 0 will give us 0. So anything to a 0 power will give us 1. So e to the 0.056 times 0 will give us 1. And 315 times 1 will give us 315. So this is the answer for A part. But they want it in billions of dollars. Now for B part, okay, this is something that is good to know. The initial value, right, is when, because now everything will be related to time. The initial value, which is the 315, will always be the initial value because 0 is a value for x, okay, or the value for t. Because when we do those application problems, we're going to have t for time, okay, which I'll explain on the next slide, on the next problem. Now for B, right, we're going to evaluate A of 12, which means I'm going to plug in 12 for the x. But here, guys, be careful with how you plug into the calculator. Make sure that the 0.056 times 12 is in parentheses, because if not, the calculator will follow PEMDAS, and PEMDAS will do the multiplication we'll do the exponent first and then the multiplication. So it's crucial to be able to put it in a parentheses, in this form. So the answer will be 616.81715575, right? Round it off, will give us something like $616.8 billion. That's the answer for B part. Now I believe this is I think this is the last slide for today. We're going to finish a little bit early for questions. But this example, I came up with this example when it was a time during COVID, because I believe COVID struck right before spring break. After spring break of 2020, everything went online. Everything was transitioned to online. So, but right before we made the transition before spring break, we were covering these problems here about exponential functions. So I decided to use the current back then the current news about how COVID was expanded here in the U.S. Right, so I use this example to show my students how we apply it in real life. It says a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. This really was more or less what was happening here in the United States. I believe the first 2 cases, they were in Washington, right? 2 people were infected. That was at the end of January, and then at the end of April, there were like 128 cases because there were the people were getting infected exponentially. So with that, we were able to come up with an exponential model in the form of y naught b to the t, with t equals 0 corresponds to the end of the month of January. Hey guys, the y naught is the initial value, same thing. Okay, so here's the problem here. A deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. Find a model of the form f of t equals to y naught b to the t power, with t equals 0 corresponding to the end of the month of January. Now, for B part, so the first part, we have to find the exponential function or model. For B part, it says if the trend continues, how many people will be infected by the end of the year? Okay, so let's see what we got here. We need to find y naught and b, right? When we find y naught and b, we found our function. So y naught is the amount present at the time equals 0. Remember the previous slide where I said when x equals 0, right, which now is going to be t, I mean, whatever the y naught is, that's the initial value. So in this case, the initial value was 2, right, because there were two cases by the end of January. So we know the value of y naught. Y naught is 2. Now, when t, here, guys, right? So this was by the end of January. So here, guys, I did like a little, like a step-by-step so you know what the second point is going to be because we have to find 2 points. When t equals 1, right, corresponds to the end of February because when t equals 0, it was the end of January. So 1 month later, we're in February. 2 months later, we're at the end of March. And 3 months later, we're at the end of April. So these are the points that we're going to be using because according to the scenario here, it says at the end of January there were 2 cases. By the end of April there were 128. So we're going to go from 0 to 3. So in 3 months from the end of January, which was the end of April, there were 128 cases. So here's what we're going to use to find B. Okay. We know that f of 3, right, that means in 3 months it was 128. And y naught is 2, right? So we know that it's going to be 128 equals to 2 to the b to the third power. Because we plugged in the 3 for t, and in 3 months there was 128, so that's why this becomes my equation now. And we have to solve for b. So the first thing we're going to do, we're going to try to isolate b by itself, right? So the first thing, we divide both sides by 2. That will give us 64, I'm sorry. So 64 equals to b to the third power. Now we're going to raise both sides to the 1/3 power. But if we do that, this, remember, now on the right side, we apply the exponential power rule, right? When we file a power to a power, we multiply the powers. So 3 times 1/3 will give us 1. And 64, right, now this one here, we convert it to a radical, remember? From an exponential to a radicand, or radical. This will be the cube root of 64 to the first power, which will give us 4. But you can plug this in the calculator how it is, and it can give you the actual answer. So we found our b. So we found the b and we found the y naught. Now let's plug them into the formula. So this is a formula for part A. Now we can predict at any given month. But here, guys, for B part, it's saying at the end of the year. Okay. So from January to December, it's going to be 11 months, right? Because the end of January to the end of December will be 11 months. So we're going to be evaluating f of 11. And we just plug in 11 for the t and put in the calculator, guys. So this is how many people will be infected. About 8,288,608 people will be infected by the end of the year. But we know there wasn't that many cases here in the U.S. There was a whole bunch, but there weren't that many. Why is that? Because this will be if there was no intervention. But we did a lot of intervention here in the U.S., right? For example, the social distance, which was 6 feet. We also began using masks. We also began using sanitizers and all that stuff, right? To try to prevent it from spreading. But if there was no intervention, more or less, this can be like an accurate estimation how many people will be infected. Okay. And I believe that's it for my PowerPoint. I hope you learned something today. And if you have any questions, let me go back to the main page here, and I can answer the questions that you might have. Thank you. Leslie, you have any questions, Leslie? You okay? Okay. Well, thank you, guys.
Thank you very much, Mr. Isasi, for the great presentation. So now you know how to change logarithms to exponents and vice versa. Make sure to join us next week also for the Tejano virtual events. And make sure to watch the videos on our YouTube playlist if you want to review any part of this lesson. Okay, let me share the next week's flyer. Okay, so for next week, February the 23rd, we'll be having a Math 1314 synthetic division and complex numbers. Math 1324 will be solving exponential and logarithmic equations. And for the 1 o'clock will be the writing center presentation. Okay, so thank you very much, Mr. Sassi. If there's no questions from the students, Albert and Leslie, you'll have a great weekend and enjoy your weekend.
Thank you, Pablo.